So what happens if you're trying to dissolve a salt in solution and it already has stuff dissolved in it? Does that affect the molar solubility of that salt? Well, it does in most cases. So we are going to take a look at what happens when we dissolve something in a solution that already has dissolved salt in it. So let's take a look at this question. What if we tried to dissolve some calcium chloride in a solution that already contains dissolved sodium chloride? And the fact that that sodium chloride is dissolved allows us to see that it will fully dissociate, or we have this fully dissociated sodium chloride in solution. So what I'm going to do is just represent that sodium chloride in the form of an equation. So I have solid sodium chloride fully dissolved, so I'm going to keep an arrow there, into sodium ions in aqueous solution and chloride ions in aqueous solution. So the stuff that I'm writing in red here is the stuff that's already dissolved in a solution, that sodium chloride. Now, what if I take this calcium chloride and I try to dissolve the solid calcium chloride in the solution that already contains that sodium chloride? What I'm going to write here is I'm going to represent this in equilibrium form. So I'm dissolving this new substance in a solution that already has something dissolved in it. Calcium chloride is in equilibrium with calcium ions and chloride ions. And the calcium chloride is in solid form and the ions are in aqueous solution form. Now what you're going to see here is an application of Le Chatelier's principle, and we're going to be looking specifically at what happens when we add a substance that's already part of the equilibrium. And you'll see that both reactions have chloride in them. So as we're dissolving this calcium chloride in water, there's already some chloride in it. And what that will do is that will shift the equilibrium to the left, or to the reactant side. And what you'll get, or what you'll see, is that the calcium chloride is less soluble in water that already has sodium chloride dissolved in it, because of the chloride that's dissolved in it. So the sodium chloride has an effect, or sort of interferes with the dissolving of the calcium chloride. Let's take a look at a practice problem. The KSP of CaF2 is 1.46 times 10 to the negative 10th, and the molar solubility in pure water is 3.32 times 10 to the negative 4th moles per liter. What is the molar solubility of CaF2 in a solution containing 0.100 molar NaF? So this solution, before we add the calcium fluoride, already has sodium fluoride dissolved in it. So let's represent the sodium fluoride in an equation form, the dissolution of the sodium fluoride in an equation form. And then let's also represent how much of each thing is dissolved. So we have 0.100 molar sodium fluoride, and it fully dissolved. And what that means is that we're going to have 0.100 molar sodium ions and 0.100 molar fluoride ions. I'm going to erase the 0.100 molar sodium fluoride because the salt is no longer exists. It's fully ionized and fully dissociated. And then what we're going to do is write the equilibrium reaction between the calcium fluoride and its ions. And this is going to be an equilibrium because this is the thing we are dissolving in the solution that already has the stuff dissolved in it. So we have the calcium ions and the two fluoride ions. So what we'll do now is we will fill in our ice table. And we have to be very careful when we fill this in, because we initially have 0.100 molar fluoride ions already in our solution. So that's going to be part of the initial concentration. Now we don't have any calcium ions in the solution, so we'll put a 0 there. The change will be exactly the same as what we're used to dealing with. We're going to add plus X for the calcium and plus 2X for the fluoride, and then we write our equilibrium concentrations in X form. So we have X, and for the fluoride we have 0.100 plus 2X. Now I'm going to write my solubility product expression. So the KSP is equal to the concentration of the calcium ions multiplied by the concentration of the fluoride ions raised to the second power. Now remember, we have to raise this to the second power because the coefficient on the fluoride ions is 2 for that equilibrium equation. Now we're going to have that, we're going to set that equal to whatever I have in my equilibrium ice box. So For the calcium ions, it's X, and for the fluoride ions, it's 0.100 plus 2X. And then I'm going to raise that to the second power because my solubility product expression had the fluoride ions raised to the second power. That's all going to equal 1.46 times 10 to the negative 10th, because that's the KSP of the calcium fluoride. So one thing I'm going to do here is, because my KSP is very, very small, it's 1.46 times 10 to the negative 10th, that tells me that calcium fluoride does not like to dissolve in water, and it's going to produce very few ions. So because that's very small, I can assume that my 2x is also going to be very, 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 very small. And if you're adding 0.1 plus something extremely small, you can just about eliminate that from the addition problem. And that makes life really easy for us, so we don't have to deal with a lot of x squared stuff and possibly the quadratic formula. So once I simplify this, I get x equals 0.100 squared equals 1.46 times 10 to the negative 10th. Now I'm going to take 0.100 and square it, and that equals 0.01. So 0.01x is going to equal 1.46 times 10 to the negative 10th. Now I'm going to take both sides and divide by 0.01 so that I can have x all by itself. So 1.46 times 10 to the negative 10th divided by 0.01 is equal to 1.46 times 10 to the negative 8th. And this is in moles per liter. So this is the molar solubility of the CaF2 in that solution that already contains sodium fluoride. Now let's compare this. This is a really low number. Let's compare this to the molar solubility of calcium fluoride in pure water, which is 3.32 times 10 to the negative 4th, which is a much larger number. That means that we can dissolve more calcium fluoride in pure water than we can in water containing that fluoride ion already. This is called the common ion effect. It means that they both have the same ion. Here's an example of this. In which solution is barium sulfate most soluble? I'm going to have you try to answer this on your own, and then we'll go over the answer. So in letter A, we already have barium dissolved in that solution. So that will make barium sulfate less soluble because the barium is already dissolved. In letter B, we already have sulfate dissolved in the solution. And in letter C, neither barium nor sulfate is dissolved, so we can dissolve the most amount of barium sulfate in solution C, the solution that contains 0.10 molar sodium nitrate. So here's our last practice problem with the common ion effect. The KSP of CaF2 is 1.46 times 10 to the negative 10th, and the molar solubility in pure water is 3.32 times 10 to the negative 4th moles per liter. What is the molar solubility of calcium fluoride in a solution containing 0.250 molar calcium nitrate? So the molar solubility in pure water is 3.32 times 10 to the negative 4th moles per liter. Now, if we have that solution that already contains calcium in it, what will that do to the solubility of the calcium fluoride? Well, it should decrease it. We should be able to dissolve less calcium fluoride in, but we can calculate exactly how much. So the equation here is calcium nitrate in solid form dissolves or breaks apart into calcium ion in aqueous solution and 2 nitrate ions in aqueous solution. So 2 NO3 negatives in aqueous solution. So that's the solution that already has the dissolved material, and how much material it has is 0.250 molar calcium nitrate, and that fully dissolves, so that's going to create 0.250 molar calcium ions and twice that amount of nitrate ions, or 0.500 molar nitrate ions. I'm going to get rid of our reactants here because it fully dissolves, and that's what we end up with in that solution. Now let's write our equilibrium reaction for the calcium fluoride. So calcium fluoride, solid calcium fluoride, dissolves or is in equilibrium with the ions, the calcium ion in aqueous solution and two fluoride ions in aqueous solution. So when we fill out our ice table, we already have some calcium in the solution. So here we are with our ice table. We have calcium ions and fluoride ions that we're going to be concerned with. And we already have 0.250 molar calcium ion in this solution. So we'll put that in our initial portion of this chart. We don't have any fluoride initially. So the change is going to be plus X for the calcium and plus 2X for the fluoride. And so for the calcium, we have an equilibrium concentration of 0.250 plus X for the calcium, and for the fluoride is 2X. Now I'm going to write my KSP, and that's going to be equal to the concentration of the calcium ion multiplied by the concentration of the fluoride ion raised to the second power. Now I'm going to substitute in my X values, so that KSP is equal to 0.250 plus X, and we'll multiply that by 2X, and we'll raise the 2X to the second power because that fluoride ion has a coefficient of 2 there. That's all going to be equal to 1.46 times 10 to the negative 10th. Now, one thing we can do here is we can assume that the X is very, very small because the KSP is very, very small. And if that X is very small, then if we're adding it or subtracting it from something, then it doesn't really do anything to that original number. So 0.250 plus a very, very, very small number is pretty much just going to be 0.250. So we're going to leave that out of the equation, the X out of the equation, and we're going to have 0.250 times 4X squared. So I kind of make the 2 squared and the X squared, and that's going to equal 1.46 times 10 to the negative 10th. Now, 0.250 times 4 is really equal to 1. And then we have our X squared, and that's going to equal 1.46 times 10 to the negative 10th. I'm just going to get rid of the 1 there because we don't really need it. And if I want to just solve for X here, I would take the square root of both sides. So the square root of X squared is X, and the square root of 1.46 times 10 to the negative 10th. Let's bring up the calculator here. And we want the square root of 1.46 times 10 to the negative 10th. And that is going to equal 1.21 times 10 to the negative 5th. And that's in moles per liter. So we cannot dissolve very much calcium fluoride in this solution. In pure water, we could dissolve 3.32 times 10 to the negative 4th, and in this solution that already contains calcium ions, we can dissolve much less calcium fluoride. So we can dissolve only 1.21 times 10 to the negative 5th moles per liter.